Okay, now let's talk about kinetic molecular theory. When we say a gas is ideal, what we're assuming is that it obeys kinetic molecular theory. So here are some basic assumptions, some of which are more true than others. But under normal pressures and temperatures like you'd have in your room, it works pretty well. Gases consist of discrete molecules that are relatively far apart. That's under Postulate 1. Gases have very few intermolecular interactions, and the volume of the gas molecules is very small compared to the gas's volume. Those things are mostly true at low pressures and room temperatures. The one that really gets you is the intermolecular interactions, as we'll find out. You can adjust for the volume of the individual molecules because it turns out that the size that you have to move around in is slightly smaller because the gas molecules themselves actually occupy space, although correcting for that is quite insignificant. But you can see that's more or less true under most conditions because the gases compress easily, and they wouldn't compress if there weren't empty spaces between them. Postulate 2 says that gas molecules are in constant random straight line motion with varying velocities. They call that Brownian motion, to straight line, bounce off the container, move in another straight line, collide with another molecule, bounce off in a straight line. Now, the gas laws we looked into earlier in the chapter are really proofs of this type of behavior. Postulate 3, gas molecules have elastic collisions with themselves in the wall of the container. The total energy is conserved during a collision. That's more or less true, but you imagine that wouldn't be perfect. But you get enough energy from the surroundings to equal out anything you lost. And the proof of that is any sealed gas doesn't exhibit any pressure drop over time. If they lost energy on each collision, they'd move slower and slower and slower until they stopped. And that's not what happens. Postulate 4, the kinetic energy of molecules are proportional to absolute temperature. That is, they're going to bounce around faster and harder and hit and collide harder if they're moving around faster, which that's what happens at a higher temperature. Kinetic energies of molecules of different gases are equal at a given temperature, and that's more or less true. Brownian motion increases as temperature increases. And you can display that in the Maxwellian distribution. What you find is that the peak is higher but narrower at a lower temperature, so more molecules are going close to the average. As it gets hot, then that bell curve spreads out. Fewer molecules are going to the average, but you do have the average does move higher, and there are more molecules moving at a faster rate of speed. So if we kind of look at these laws and see how they work in context of kinetic molecular theory, for example, Boyle's law, the pressure and the volume are inversely proportional. If the volume increases, for example, then the collisions with the container walls per capita decrease, and therefore the pressure would decrease. Dalton's law says that the total pressure is additive. Since there are very few intermolecular reactions, the pressure is just based on the number of moles of gas trapped in the container. And since they move more or less independently of one another, we can say then that it would not work. It's not going to have any more complex interaction than that. Charles's law, volume is proportional to temperature. If I increase the temperature, I'm going to increase the kinetic energy of the gas molecules and increase their velocities. They're going to collide with the walls with more force because they're moving faster. So to keep that pressure the same, then it must increase. That's sort of your hot air balloon effect. Let's look at a study question then. So what are idealized assumptions? We assume all those, and the ones that we're going to focus on are the intermolecular interactions and the volume of the gas molecules. We're going to focus on those two as we move forward. And we're going to assume that there are no interactions, even though there probably are some. We're going to assume the volume of the gas molecules is zero, even though it's really not zero. And sometimes those assumptions are better than others. Diffusion and effusion. Diffusion is the intermingling of gases. That if you were to spray something in the air that had an odor, people closest to the source would smell it first. People farther away would smell it after, because those gas molecules actually have to move through the air and you have to inhale them before you can smell it. Effusion is the escape of gases through tiny, tiny holes. For example, helium will escape more quickly through a rubber balloon with bigger pores than a mylar balloon with very small pores. Regardless, if you look at it per gas, the rate of diffusion or effusion is inversely related to the square root of the molar masses, or the square root of the densities. Which what that means, if you got a higher molar mass, it will diffuse or effuse more slowly. So which gas will diffuse or effuse more quickly? Helium or sulfur dioxide at the same temperature and pressure. Under the same conditions, it's going to be the helium that's going to diffuse or effuse more quickly because it has the lowest molar mass. There's one I'll leave for you to work. Let's talk about real gases then. Real gases can behave more or less ideally at ordinary temperatures and pressures, and you find the correction is actually quite small under those conditions if you were to try to correct it. At low temperatures, particularly the intermolecular attractions are going to be a problem, and at high pressures you're forcing them to be close together and cause interactions to be more likely. So the real reasons you deviate from ideality is if the molecules get close together, their volume becomes important. Not as big of a correction as you would think, but it can be corrected. Ironically, the easiest of the two to correct. If you get at low temperature, then those interactions are more significant because you have less energy to break those interactions and keep the molecules going. The molecular interactions are going to become very important as well. Some gases interact with one another more so than others. That becomes a more important correction. And so you can correct the ideal gas law by adding a term to the pressure and subtracting a term from the volume. So what that means is that the pressure is underestimated a little bit. That is, as the gas molecule is going toward the wall of the container, it interacts with another molecule and slightly reduces the force with which it collides with the wall, therefore reducing the apparent pressure. So we have to add a term to the pressure to make that work out. Now, as we mentioned before, we've been ignoring the volume of the gas molecules themselves, and so that NB is the number of moles of gas times the molar volume of just the gas molecules, not the empty space, and so you can correct for the percentage of the volume occupied by that. And then the other side is the same. We're not going to do any calculations with this, but you should understand the nature of the corrections. Those A and B constants you have to look up for each gas, and there's a table in your text. So A is going to help you account for the intermolecular attractions. B is going to account for the volume of the molecules. Gases that are nonpolar behave more ideally. Gases that are polar are going to have higher rates of interaction. The interaction is going to be stronger, and it's going to behave less ideally, as you might imagine it would. So nonpolar gases have weaker forces of attractive forces called London forces, which we'll talk about at a different time, but very weak forces of interaction. Polar gases have dipole-dipole attractions because they're polar and they have a dipole moment, or they form things like hydrogen bonds. They have very strong forces of attraction, and that's going to make the difference.